Good morning. Thank you everyone for attending this presentation. We're going to be talking about waves and optics for level 3 students. Although we encounter waves every day, many people are unaware of just how important they are. Waves allow us to communicate using mobile phones and Wi-Fi, transmit television and radio signals, use fibre optic internet, diagnose disease using medical imaging, and even carry out modern dental treatments. Throughout this presentation, I will explain how not only what waves are, but why they behave in the ways they do. As we move through each slide, I will refer to the diagrams in all of the presentations and the concepts that relate to the theory to practical applications. By the end of today's presentation, you should understand how waves are generated, how different wave types behave, and how scientists describe waves mathematically. I will explain reflection, refraction, Snell's law, total internal reflection, polarization, the electromagnetic spectrum, interference, and diffraction. Rather than simply memorizing definitions, it is important to understand why these phenomena occur, because understanding allows us to apply physics to solve real-world problems in medicine, dentistry, engineering, and communications. A wave begins when a source of energy causes a disturbance. If we imagine dropping a stone into a pond, the stone transfers energy into the water, creating ripples that move away from the point of impact. Although the ripples appear to travel across the surface, the individual water particles mainly move up and down around their original position. This is an important concept because waves transfer energy without causing the material itself to travel over long distances. Mechanical waves require a material medium because neighbouring particles collide or interact with one another, passing energy from one particle to the next. Examples include sound travelling through air, seismic waves travelling through rock, and ripples travelling across water. Electromagnetic waves behave differently because they are produced by oscillating electric and magnetic fields. They therefore do not require particles and can travel through the vacuum of space. This explains why sunlight is able to travel approximately 150 million kilometres from the sun to Earth. Understanding how waves are generated forms the foundation for every other topic in wave physics, because all wave behaviour begins with the transfer of energy from a vibrating source. The diagram here compares the two main types of wave. In a transverse wave, the oscillations occur at right angles to the direction of travel. Visible light and every other electromagnetic wave are transverse. This property is particularly important because only transverse waves can be polarized, which we will discuss later. Longitudinal waves are different because the oscillations occur parallel to the direction of travel. Instead of peaks and troughs, they consist of compressions where particles are close together and rarefactions where particles are further apart. Sound waves are the best known example. A useful way to remember the difference is to imagine shaking a rope up and down to create a transverse wave, compared with pushing and pulling a spring to create longitudinal waves. This simple comparison helps students visualize particle movement and is commonly used in physics teaching. Mechanical and electromagnetic waves both transfer energy, but they do so in different ways. Mechanical waves rely on particles interacting with one another, meaning they cannot travel through a vacuum. If there is no particles, there is no mechanism for transferring the disturbance. Electromagnetic waves, however, consist of oscillating electric and magnetic fields that continually regenerate one another as the wave travels. This allows them to travel through empty space at approximately 300 million meters per second. Examples of electromagnetic waves include radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays and gamma rays. Although they all travel at the same speed in a vacuum, they differ in wavelength, frequency and energy. These differences determine how each region of the electromagnetic spectrum is used, from broadcasting radio programs to diagnosing disease and treating cancer. This slide introduces some of the most important mathematical relationships in wave physics. Frequency is the number of complete waves passing a fixed point every second and is measured in hertz. Time period is the time taken for one complete wave to pass and is measured in seconds. These qualities are inversely related, meaning that as frequency increases, the speed time period decreases. The wave equation links wave speed, frequency and wavelength. It allows scientists to calculate unknown quantities when two of the three variables are known. The equation has applications across science and engineering, including telecommunications, acoustics and medical imaging. When answering examination questions, it is important to write the equation first. Substitute the values carefully, include the correct units and round the answer appropriately. Understanding what each variable represents is much more valuable than simply memorizing the equation, because it allows you to explain how changing frequency or wavelength affects wave speed in different situations. Phase difference describes how far apart two waves are within one complete cycle. A full wavelength corresponds to 360 degrees or 2 pi radians. Waves that are in phase have a phase difference of 0 degrees or multiples of 360 degrees, meaning that their peaks and troughs line up perfectly. When these waves meet, they reinforce one another, producing constructive interference. If the phase difference is 180 degrees, the peak of one wave coincides with the trough of another, producing destructive interference and reducing or completely cancelling the wave. If we look closely at the diagram here, we can see that one complete wavelength represents 360 degrees, or a full circle, or 2 pi radians. The two waves are shown starting at different positions within the wave cycle. When the peaks and troughs line up perfectly, the waves are described as being in phase. When the peak of one wave lines up with the trough of the other, the waves are completely out of phase, with a phase difference of 180 degrees. The visual representation makes it much easier to understand how waves can either reinforce one another or cancel each other out. Although this concept may seem abstract, it explains many everyday phenomena, including noise-cancelling headphones. These devices generate a sound wave that is almost perfectly out of phase with background noise, reducing the overall sound reach in the ear. Understanding phase difference is therefore important in both engineering and medical technology. We now move on to reflection and refraction. Reflection occurs whenever a wave meets a boundary and is unable to pass through it completely. The law of reflection states that the angle of incidence always equals the angle of reflection, provided both angles are measured from the normal. This predictable behaviour allows mirrors to form accurate images. Looking at the ray diagrams here, notice that the refracted ray leaves the surface at exactly the same angle that the incident ray arrived. The incident ray, the refracted ray, the reflected ray. As the light leaves the glass, it speeds up again and bends away from the normal. It is also worth remembering that although the speed and wavelength change, the frequency of the light remains constant. Refraction occurs when light passes from one medium to another with a different optical density. Because the speed of light changes, the wave changes direction. Light slows down when entering glass from air and bends towards the normal. When it leaves the glass and speeds up, it bends away from the normal. Refraction explains why objects appear bent when placed in water and is fundamental to spectacles like glasses, microscopes, cameras and optical instruments used throughout healthcare. We now move on to Snell's law. Snell's law provides the mathematical relationship between the angle of incidence, the angle of refraction and refractive index. Refractive index is a measure of how much a material slows down light compared with a vacuum. Materials with higher refractive incidences bend light more strongly. If we examine the diagram here, the dashed line represents the normal, which is drawn at 90 degrees to the surface. The angle of incidence is measured between the incoming ray and the normal, while the angle of refraction is measured between the refracted ray and the normal. Snell's law can also be rearranged to calculate unknown refractive indices or unknown angles, making it one of the most useful equations in optics. Scientists and engineers use Snell's law when designing lenses because different curvatures alter the way light is focused. In healthcare, it enables microscopes to produce highly detailed images and allows corrective lenses to compensate for short and long-sightedness. Without Snell's law, many modern optical technologies would not exist. Very important. We now move on to total internal reflection. Is one of the most important applications of wave physics. It only occurs when light travels from a material with a higher refractive index into one with a lower refractive index and strikes the boundary at an angle greater than the critical angle. Under these conditions, all of the light is reflected back into the material instead of escaping. This diagram here illustrates how the light repeatedly reflects from the inner surface of the optical fibre instead of escaping. Each reflection keeps the light trapped inside the fibre, allowing information to travel enormous distances with very little energy loss. This is why fibre optic communication is capable of transmitting huge amounts of data quickly and reliably. This principle is the basis of fibre optic communication. Light repeatedly reflects along the fibre with very little energy loss, allowing enormous amounts of digital information to travel around the world at extremely high speeds. In dentistry, fibre optics are incorporated into curing lights and illuminated handpieces, while medicine uses flexible fibre optic endoscopes to visualize internal organs with minimal invasive surgery. I'll move on to polarization. Polarization occurs when vibrations are restricted to a single plane. Only transverse waves can be polarized because their oscillations occur perpendicular to the direction of travel. Longitudinal waves, such as sound, cannot be polarized because their vibrations occur parallel to the direction of travel. Looking at the illustrations here, the incoming light vibrates in many different planes. After passing through the polarizing filter, only vibrations in a single plane remain. This simple visual explains why polarized sunglasses reduce glare so effectively, because they block much of the horizontally polarized light reflected from flat surfaces. Polarizing filters are used wisely to reduce glare reflected from water, roads and snow. Photographers use them to improve image quality by increasing contrast, while LCD screens rely on polarized light to produce clear images. We now move on to the electromagnetic spectrum, which consists of radio waves, microwaves, and we go down cosmic rays. Although every electromagnetic wave travels at the same speed in a vacuum, each differs in wavelength, frequency, and energy. If we follow the spectrum from left to right, notice that the wavelength becomes progressively shorter while the frequency and energy steadily increase. This diagram demonstrates that all of these waves belong to one continuous spectrum rather than existing as completely separate forms of radiation. This also explains why radio waves are suitable for communication, whereas the much higher energy X-rays and gamma rays can ionize atoms and therefore require careful safety precautions. Radio waves have the longest, at the end, wavelengths and lowest energies, making them ideal for communication. Microwaves are used in satellite communication, radar, and cooking. Infrared radiation is associated with heat and is used in thermal imaging. Visible light represents only a tiny part of the spectrum, but allows human vision. Ultraviolet radiation is valuable for sterilizing equipment, but excessive exposure to this damages DNA. X-rays penetrate soft tissues while being absorbed by bone, making them invaluable in medicine and dentistry. Gamma rays possess the highest energies and are used to destroy cancer cells during radiotherapy. Each region of the electromagnetic spectrum has been developed for specific technological applications. Mobile phones, televisions, and GPS rely on radio waves and microwave applications. Mobile phones, televisions, and GPS rely on radio waves and microwaves. Thermal cameras use infrared radiation to detect heat. Optical fibers transmit visible and infrared light. And as we can see from the diagram here, the different uses and applications of the electromagnetic spectrum. Thomas Young's double slit experiment, first performed in 1801, provided convincing evidence that light behaves as a wave. When coherent light passes through two closely spaced slits, the waves spread out and overlap. Where peaks meet peaks, constructive interference produces bright fringes. Where peaks meet troughs, destructive interference produces dark fringes. This experiment transformed scientific understanding of light because it challenged the earlier belief that light behaved only as particles. It remains one of the most important demonstrations in the history of physics. Looking carefully at the diagram, each slit behaves as a new wave source. Diffraction describes the spreading of waves after passing through a gap or around an obstacle. The amount of diffraction depends upon the relationship between wavelength and gap size. The closer the gap to the wavelength, the greater the spreading effect. This diagram here shows wavefront spreading after passing through a narrow opening. Notice that the spreading becomes much greater when the opening is smaller in size than the wavelength. Now move on to diffraction. Practical experiments compare measured diffraction patterns with theoretical calculations. Agreement between the two increases confidence that the experiment has been performed correctly. Differences may result from measurement uncertainty, equipment limitations, inaccurate alignment, or environmental influences. Looking at the data, the measured values are compared with the theoretical calculations. Small differences are expected because of measurement uncertainty, equipment limitations, or slight alignment errors. Considering these possible sources of error demonstrates scientific evaluation, which is an important part of experimental physics. Evaluating these errors demonstrate scientific thinking because it shows that experimental results should always be interpreted critically rather than accepted without question. Thank you for listening. So we have a summary here, and please go through the references at the end. Thank you for listening.